What forces unleash the monstrous power of volcanoes and earthquakes? What processes form Earth's mountains, its rocks and boulders, and the minerals and fuels deep within it, which we mine and use? What processes form the fertile soils that produce our food? The answers to these questions lie in Earth's crust, the thin, ever-changing, outermost layer of our planet. Throughout our history, scientists have been trying to understand the forces that shape and change Earth's crust. In this unit, you will see how theories about Earth's crust were developed and then discarded as scientists made new observations and saw new connections between their past observations. You will see how recent technologies, which allows scientists to see the seafloor and to X-ray Earth's interior, has led to the current theory of a shifting crust. You will also have a chance to think about how our demands for food, minerals, and fuels harm Earth, and to consider how we might better take care of Earth's resources. Chapter 10, Minerals, Rocks, and Soils. Where Earth meets sea and sky, rocky coasts from one of the most majestic landscapes in the world, Peggy's Cove in Nova Scotia. Here, waves crash endlessly against the boulders and spray reaches up to touch the lighthouse. Nearby, lush fields unfold in green and golds. Is there any connection between the barren rocks and the fertile farmland? If there is a process that changes the rocks to farmland, does the process end there, or does it continue? What valuable materials are buried in the ground? How do they get there, and why are they important to us? Canada is rich in beauty and scenery, and in natural underground resources. It is a leading exporter of forestry, mining, and agricultural products which depend on the rocks, minerals, and soils of Earth's crust. The gifts of Earth give Canadians strong economic support, but they will not last forever. It is important that we, as Canadians, manage these gifts wisely so that they will be available for us and for future generations to use and enjoy. In this chapter, you will learn about the minerals, rocks, and soils on or near Earth's surface, and find out about some of the processes that form them. You have been examining a number of items to decide which ones could be classified as rocks. What is rock? Rock is made up of one or more pure, naturally occurring, non-living, solid materials called minerals. Most minerals are quite rare. Only a few, such as quartz and mica, are common, found throughout Earth's crust, the thin outermost layer of Earth. A mineral can be an element, a pure substance, or a compound, two or more substances. Quartz, for example, consists of the elements silicon and oxygen. No other mineral has these elements in the same arrangement and proportion. Sulfur, copper, gold, and diamond, on the other hand, are made up of a single element. If you were a prospector digging for gold, how would you know if you had found it? No problem, you say? We all know what gold looks like, or do we? Another mineral, pyrite, which is more common than gold, is almost identical to gold in appearance. The value of gold is high, while pyrite is almost worthless. How could you find out? if that shiny yellow metal you found is really gold. There are important clues in the properties of minerals. Figure 10.1. Granite is a rock that is made up of an assortment of minerals. It is often polished and used in buildings and at the base of statues. Granite contains the mineral feldspar, sparkling grains, quartz, a glassy crystal, mica, greenish-gray flakes, and hornblende, dark flakes. The Mohs hardness scale. You are probably aware that you can scratch a piece of chalk with your thumbnail, but you cannot scratch most other rock samples in the same way. How can a substance's scratchability be used for mineral identification? This is a question that a German scientist, Friedrich Mohs, asked himself in 1812. He developed a scale of 10 minerals with a hardness value of 1 to 10. See table 10.1. How do you use the scale? Suppose that you have an unknown mineral that looks like talc or corundum. Scratch it with your fingernail. If it is talc, it will scratch easily because your fingernail has a hardness value of 2.5 on the scale, much harder than talc, which has a hardness value of 1. If it does not scratch easily, it cannot be talc and must be corundum instead. The hardness of corundum is more different and difficult to test because corundum is so hard. It is harder than most other objects and minerals. What could you use to test the hardness of corundum? Diamond is the hardest mineral. One of its uses is shown in figure 10.2. 10.2, although the glass cutter wheel looks like ordinary metal, its edge is actually embedded with a hard mineral, such as diamond. Corundum is also used in countertops in kitchens. The Mohs hardness scale is a useful tool for mineral identification. Given that there are over 3,000 minerals, however, other properties are also needed to identify them. Minerals sometimes occur as crystals. A crystal occurs naturally and has straight edges, flat sides, and regular angles. All of the minerals in Earth's crust can be grouped according to the 6 different crystal shapes shown in table 10.2. Let's go back for a moment and look at table 10.1. It has several minerals. It has talc is number 1, gypsum is number 2, calcite 4, apatite is 5, feldspar is 6, quartz is 7, topaz is 8, corundum is 9, and diamond 10, the hardest. Hardness of common objects. A soft pencil point is 1.5. Your fingernail is 2.5. A piece of copper, you would think would be harder, but it's actually 3.5. An iron nail is not terribly hard relative to some minerals. It's only 4.5. Glass is harder than an iron nail at 5.5. A steel file is 6.5. A stake plate, go figure, is a 7. Sandpaper, you wouldn't think that would be very hard, but that's a 7.5. And emery paper, often used for fingernail filing, is a 9.0. Table 10.2, the 6 major crystal systems. Halite, and the system is cubic. Wulfenite, it is tetragonal. Topaz is orthorhombic. Gypsum, monoclinic. And albite is triclinic. Other clues to mineral identification. Luster. You have just seen that a mineral's crystal structure provides an important clue to its identity. Some minerals, such as gold and other metals, appear shiny. Other clues to mineral identification. Luster, you have just seen that a mineral's crystal structure provides an important clue to its identity. Some minerals, such as gold and other metals, appear shiny. Another clue to their identity. Others, such as talc, can appear dull. Most dull minerals are nonmetals. The shininess or luster of a mineral depends on how light is reflected from its surface. The surface of a mineral can reflect light in many different ways. Color. Next to luster, color is one of the most attractive properties of minerals. The color of a mineral can also be a clue to its identity. As in the case of gold and pyrite, however, color alone cannot identify a mineral. In addition, not all minerals are the same color all of the time. For example, the mineral corundum, made of aluminum and oxygen, is white when pure. However, when it contains iron and or titanium, it is blue and is called sapphire. When it contains chromium, it is red. Figure 10.3. Oriental emerald green, amethyst purple, and topaz yellow are other colored varieties of corundum due to impurities. Streak. When a mineral is rubbed over a piece of unglazed porcelain tile, as in Figure 10.4, Figure 10.4, color is not always useful for mineral identification. Hematite, for example, can be dark red, gray, or silvery in color. Its streak, however, is always dark red-brown. A streak is the color of the powdered form of the mineral. Lookalikes, such as gold and pyrite, can be distinguishable using a streak test. Gold leaves a yellow streak, while pyrite has a greenish black or brown black streak. Minerals with a greater hardness than the porcelain tile, hardness value of 7, will not leave a streak. Such minerals, especially the black ones, can be crushed into powder. A surprising number of black minerals have lighter colored powders. Cleavage and fracture. Hardness, luster, color, and streak are mineral properties that help geologists to identify many minerals fairly easily. Cleavage and fracture. Hardness, luster, color, and streak are mineral properties that help geologists to identify many minerals fairly easily. Other properties provide further clues to their identity. Cleavage and fracture are two very useful ones. The way a mineral breaks apart can be a clue to its identity. If it breaks along smooth, flat surfaces or planes, it is said to have cleavage. Mica is an example of a mineral with cleavage. See Figure 10.5a. 10.5a. Mica is a mineral with a single cleavage direction that allows it to be pulled apart into sheets. Separating the layers of mica is like separating the pages in a book. Not all minerals have cleavage. Minerals that break with rough or jagged edges have fracture. See figure 10.5b. 10.5b. Obsidian is a mineral that fractures when broken apart. Obsidian is an example of a mineral with fracture, while separating the layers of mica is like separating the pages of a book. Breaking apart quartz is like ripping a book in half. Uses of minerals. Why are minerals so important? As you have seen so far, minerals have certain properties that make them valuable and useful. For example, gems are highly prized minerals because they are rare and beautiful. Many gems, which are brighter and more colorful than common samples of the same mineral, are cut and polished for use in jewelry. Diamond, a valuable gem, also has practical uses. Because diamonds are the hardest of all minerals, no naturally occurring minerals can scratch a diamond except another diamond. They are used in drill bits and other instruments to cut through hard substances, such as steel and rock. Scientists are able to apply tiny rows of diamond on the edge of surgical scalpels, razor blades, dental drills, diamond-tipped phonograph needles, and diamond-coated computer parts. Metals are among the most useful minerals. See figure 10.7. Titanium is as strong as steel and 45% lighter, making it especially suitable for use in aircraft and spacecraft. We use them in cars, appliances, and many household utensils. Metals are single elements, such as gold, silver, copper, aluminum, nickel, and iron. Metal deposits occur naturally in rocks, where they are mixed with other mineral deposits. Rocks that are rich in metals and metal oxides are called metallic ores. 10.6, I left that out. Figure 10.6 shows a picture of polished and unpolished amethyst. More uses of minerals. Iron, zinc, copper. You might think of these in terms of appliances and utensils, but what do they have to do with your body? They are important for health. In order to survive, your body needs over 20 kinds of elements found in minerals. For example, iron from such minerals as magnetite and pyrite helps blood carry oxygen. Calcium, found in calcite and dolomite, helps to make bones and strong teeth. Sodium, found in halite, helps to regulate water in the body's cells. Some of the vegetables and grains that we eat are rich in minerals. Like you, crops need minerals to survive and stay healthy. Farmers must find ways to return minerals that crops have used up in the soil. A common method is to apply fertilizers. Organic fertilizers are made from plant and animal remains and waste. Inorganic fertilizers are made from essential elements and minerals. Another method of preserving or returning minerals to the soil is crop rotation. Farmers plant a different crop in each field each year. This ensures that the minerals used by one crop are replaced the following year by a different crop. For example, soybeans will replace nitrogen that a previous crop has used up. See figure 10.8. Figure 10.8, this soybean crop is rich in calcium. Calcium in the soil dissolves in water and passes into the roots of the plant. Minerals have many other practical uses. When quartz is stimulated with an electric charge from a battery, it vibrates more than 30,000 times each second. Because the vibrations are so regular, they keep time very accurately. Today, tiny pieces of quartz are used in most watches and timepieces. Minerals that fluoresce have been used in the hands and numbers on clock and watch faces. See figure 10.9. Some minerals can fluoresce, glow, under ultraviolet light or X-ray beams, and some can continue to glow, phosphoresce, for a short while after the light is removed. Rocks and the rock cycle. Rock families. As you have seen, rocks are made of minerals. In this section, you will examine how rocks and minerals form. Scientists have grouped rocks into three major families or types based on how they form. The three families are igneous, sedimentary, and metamorphic rocks. Each can usually be identified by its appearance. Igneous rock. Igneous rock forms when hot magma and when hot lava cool and solidify. Magma is melted rock found below Earth's crust, where temperatures and pressure are high. Any rock that is heated at great depths can melt into magma. Under high pressure, the magma can push away or dissolve the surrounding rock, making room for itself. Sometimes fingers of hot magma push into the surface through cracks in Earth's crust. Geologists classify igneous rock based on whether it has formed above or below Earth's surface. Magma can cool and harden below the surface. The resulting rock is called intrusive rock. Granite is an example of an igneous rock that formed very deep and very slowly in Earth's crust. When magma breaks through Earth's surface in the form of a volcanic eruption, it is called lava. Rock that formed when lava cools on Earth's surface is called extrusive rock. See figure 10.11. 10.11, it says this diagram shows two main types of igneous rock and how they formed. It shows intrusive and extrusive rock forming. 10.10, it says the Balancing Rock on Long Island near Tiverton in Nova Scotia is a spectacular basaltic sea stack. How might it have formed? Magma can contain solidified crystals that can be seen in solidified rock. The appearance of the crystals in igneous rock samples can differ depending on how fast the rocks cooled. Write a hypothesis about speed of cooling and size of crystals and test it in the next investigation. Sedimentary rock. As its name indicates, sedimentary rock is made from sediment, loose material such as bits of rock, minerals, and plant, and animal remains. These sediments become closely packed and cemented together. Figure 10.12. In this gorge, layer upon layer of rock is visible. Rocks that break away from this rock face will have layers. These layers provide clear evidence of how sedimentary rock forms. Sedimentary rock makes up about 75% of all rock we can see on the Earth's surface. Igneous rock occurs mostly below Earth's surface. How does sedimentary rock form? Why do the fragments separate into layers? See if you can find some answers in the next activity. Formation of sedimentary rock. As you saw in the activity, rock sediment eventually settles, and over the years, it starts to pile up. Most often, this happens in lakes and oceans, where the larger, heavier fragments settle first and end up near the bottom. Sometimes wind, ice, or gravity move sediments to a place where it settles. As sediment slowly settles on top of other sediments, the rock takes on a layered appearance. These layers are called beds. How does settled sediment become rock? Each layer of sediment is squeezed together by the weight of the other sediment and the rock on top of it. This process is called compaction. In some rock, minerals dissolve as the water soaks into the rock, forming a natural cement that sticks the larger pieces of sediment together. See figure 10.13. Cement is used to bond or glue rocks and bricks together in building construction. Roman cement was a mixture made from equal portions of lime, calcium oxide, and volcanic ash, or crushed tiles, mixed with water. Many buildings, like the famous Colosseum in Rome, were made from huge rocks glued together thousands of years ago with long-lasting Roman cement. Limestone is one of the most common and useful sedimentary rocks. It is also unique because many types are made up of large amounts of sediment from the remains of once living things called fossils. For this reason, limestone is in a separate class, organic sedimentary rock. Ocean animals, such as mussels and snails, make their shells mainly from the mineral calcite. When the animals die, their shells accumulate on the ocean floor, where most sedimentary rock is born. The appearance of a sedimentary rock can reveal what type of sediment formed it. Figure 10.14. A. Shale or mudstone is sedimentary rock formed from fine grains of clay or mud. 10.14b. A harder, rougher rock called sandstone is formed from larger granules of sand, mostly made up of quartz. 10.14c. Rounded pebbles and small stones cemented together form a type of rock called conglomerate. Metamorphic rock. Once a rock is made, can it change its form? The answer is yes, it can. Geologists have found rocks that resemble certain igneous or sedimentary rocks, but differ from them in significant ways. Look at the rocks in figure 10.15. Shale can become slate, and limestone can become marble. What causes these changes? Slate and marble are just two examples of the third family of rock called metamorphic, meaning change form. Rock. This rock may be formed below Earth's surface when extremely high pressure and heat cause the original rock or parent rock to change form. This type of rock formed depends on the amount of pressure applied. Shale, for example, can undergo several changes as pressure and temperature increase over time. This change results in the formation of slate, then schist, then gneiss from shale. Metamorphic rock can change so completely that it no longer looks like the parent rock, but there are enough common characteristics that geologists know the two are related. For example, limestone and marble look different, but both have a hardness value of 3, and both are made of the mineral calcite. Figure 10.16 shows how granite can be changed to form another rock, gneiss. Igneous granite can lie in large bodies deep below Earth's surface. Diagram B shows what can happen to the mineral grains of granite as the pressure of heavy, overlying rock squeezes them together. Gneiss, the altered rock in this process, is an example of metamorphic rock. Figure 10.16. A, granite, igneous. Then you have B, heat and pressure. And then C, gneiss, metamorphic. Figure 10.16, the change from igneous rock to metamorphic rock is a long, slow process caused by heat and pressure over time. The rock cycle. Much of what you learned so far in this section suggests that rocks are constantly changing. For example, igneous rock is formed when magma or lava cool. Rock fragments and sediments can be compacted and cemented to form sedimentary rock. And both igneous and sedimentary rock can form metamorphic rock under high pressure and heat. Does the process stop there? No. Rocks continue to change in an ongoing process called the rock cycle. See figure 10.17. All right, this is a little bit involved. The picture shows a volcano with a cutaway of the mountain and a cross section of the crust and apparently, possibly deep into the crust. It says in figure 10.17, this model of the rock cycle shows the part that volcanoes play in the rock cycle. Note that the diagram is not to scale. The production of new magma occurs 25 to 40 kilometers below Earth's crust. Now, in the picture, you have a variety of identifications. It shows melting magma source of igneous rock. And then you have in the ocean floor, looks like on the continental shelf, sedimentary rock becomes metamorphic rock very gradually at depths of 5 to 25 kilometers. And then you have heat and pressure. And then you have compaction and cementation. You have weather and erosion. And you have the volcano erupting, etc. Okay. Does the magma ever run out? As rocks sink back into the depths of Earth's crust, the heat and pressure can turn them back into magma. As well, all rocks can be broken down to smaller rocks, fragments, and sediment. Although human activity is responsible for some of the breakdown process, most of it occurs naturally. Weathering. Sediment comes from larger rocks that have broken down or worn away by a natural process called weathering. Rocks can be weathered mechanically, chemically, or biologically. Mechanical weathering. Mechanical weathering is the physical breakup or disintegration of rocks. For example, gravity causes rocks to fall down a cliff and break apart. Rocks rolling down a slope or in a fast-moving stream rub and bump against each other, becoming smoother and more rounded. Climate change can also cause mechanical weathering. In early spring or during winter warm spells, as days begin to get warm, nighttime temperatures still dip below freezing. This is known as the freeze-thaw period, and it can go on for several days. During the freeze-thaw period, snow and ice melt in the daytime, allowing water to seep into cracks in rock. At night, when the temperature falls below 0 degrees Celsius, the water freezes and expands, pushing the cracks wider apart. Each day, more water fills up the cracks, and it freezes again at night, pushing the rock pieces farther apart. Finally, the rock breaks apart. If a rock has many cracks, it can seem to crumble at the end of a freeze-thaw period. This entire process is called frost wedging. See figure 10.18. Frost wedging is caused by water that repeatedly freezes and thaws. In the picture, you see water freezing in cracks, expands, widens the cracks, and eventually you have the rock breaking. Materials other than water, such as crystal salts, can wedge rocks apart as well. Another type of mechanical weathering occurs when wind and water wear away the surfaces of rocks and carry the pieces to another place, where the pieces build up. Erosion is the part of the process responsible for wearing away, and deposition is the part of the process responsible for building up. A dust storm and the muddy silt along a river bed are examples of erosion and deposition. See figure 1019A and B. Blowing dust and sand granules are carried from one place to another, and B, the impact of a single raindrop loosens many soil particles. Erosion occurs more easily when small pieces of grit that are suspended in the wind and water act like sandpaper on Earth's surface. During the Ice Age especially, the northern lands, such as Canada and Scandinavia, and their glaciers flowed across Earth's surface, carving and scraping and lifting away rock and soil. See figure 10.20. The glaciers carried the sediment far away. When they finally began to melt and retreat, they deposited the sediments in new locations. Figure 10.20. Which way did the glaciers go? The straight line scratches you see on the surface of the rock continue across the cracks. They are therefore not a characteristic of the rock itself, but they were caused by something heavy and large that scratched only the surface. Chemical weathering. Chemical reactions can speed up the process of erosion. Chemical weathering involves the breakdown or decomposition of minerals as a result of the chemical reaction with water, with chemicals dissolved in water, or with gases in the air, such as carbon dioxide and sulfur dioxide. That's acid rain. An example of a chemical reaction is acid rain, which contains dissolved chemicals from air pollution. This chemical rainwater reacts with some rocks. The rock material dissolves easily in the acid water and washes away. See figure 10.20. 10.20. Many old and valuable marble statues and buildings in Europe and Asia have suffered the effects of acid rain and have had to be repaired. The Parthenon in Athens, Greece, is shown here under reconstruction. It was also bombed during World War II, so I'm not sure how accurate that picture is, and it's misleading. Biological weathering. Biological weathering is the physical or chemical breakdown of rock caused by living organisms, such as plants, animals, bacteria, and fungi. Physical breakdown occurs, for example, when a plant root wedges into a rock by forcing its way into a crack, just as frost does. As the root grows and expands, so does the crack, and the rock pushes apart until it eventually crumbles and breaks. As well, chemical reactions can take place between the rock material and acidic fluids that are produced by plant roots, bacteria, fungi, and some insects and small animals. As the rock slowly dissolves and flows away with rainwater, cracks and crevices increase in size until the rock finally breaks apart. See figure 10.22. Figure 10.22, tree roots work their way into cracks and, as they grow, eventually break up the rock. The physical environment, which includes natural processes such as weathering, earthquakes, volcanic eruptions, has an impact on the rock cycle. If the physical environment changes, the rocks in it will also change. Mechanical, chemical, and biological weathering work together constantly to change the landscape around us. It's not just one kind of weathering. Oftentimes, it is a combination of several different types of weathering. Soil. Sediment is an in-between stage in the rock cycle. The slow process of rock formation takes thousands of years to occur. What happens to sediment in the meantime? Rock sediment is commonly called dirt, but what most people call dirt is actually soil. Soil is a mixture of weathered rock, organic matter, mineral fragments, water, and air. Formation of soil. How does soil form? Earth is covered by a layer of rock and sediments. Sediments and mineral fragments do not become soil until plants and animals have lived in them and added organic matter such as leaves, twigs, dead worms, and insects. The organic matter creates spaces that can be filled with air and water. All of these combine to form soil, a material that can support plants. See Figure 1023A, B, and C. Figure 1023A. These weathered rock fragments contain many cracks and spaces, providing areas that air and water can fill. B. Immature soil can support small, hardy plants that attract insects and other small animals. Over time, dead plant and animal material build up, and bacteria and fungi cause them to decay. The decaying organic matter forms a layer on top of the weathered rock. Figure 1023C. Mature soil contains mineral-rich clay on top of weathered rock. The clay forms when water carries the minerals away from the decaying organic matter above. Above the clay, the topsoil extends to the surface and contains decayed organic matter, plant roots, and living organisms. Climate, the type of rock, and the amount of moisture influence soil formation. Even the slope of the land can influence it. For example, if the slope is steep, loose dirt will run off with each rainfall, leaving only large, barren rocks. In addition to these non-living factors, the small living creatures that invade the soil can speed up the process of soil formation. As you saw in Unit 1, soil is a complex ecosystem where small rodents, worms, insects, algae, fungi, bacteria, and decaying organic matter all live in harmony. Most of the decaying matter is made up of dead plant matter called compost. It mixes with other matter to form the dark-colored portion of the soil called humus. Humus is rich in nutrients such as nitrogen, phosphorus, potassium, and sulfur. These nutrients dissolve in water in the soil. Plants absorb the nutrient-rich water through their roots. Humus also promotes good soil structure and helps keep the water in the soil. As worms, insects, and rodents burrow throughout the soil, they mix the humus with fragments of rocks. In good quality soil, there are equal parts humus and broken down rock. A fertile soil is one that can supply nutrients for plant growth. Soils that develop near rivers are generally fertile. Some soils may be nutrient poor and have low fertility, such as the eroded rocky soil of steep cliffs and roadsides. Soil profiles. Soil can take thousands of years to form. They can range in thickness from 60 meters in some areas to just a few centimeters in others. Soil varies in structure and appearance, depending on its depth. In examining soil, scientists have exposed layers of soil with clear differences in appearance and composition. The layers of soil make up a soil profile. The soil profile in Figure 10.24 illustrates how the layers are divided. They show different degrees of soil evolution. Examine Figure 10.24. The top layer, A, is called topsoil. It consists of dark-colored, rich soil that contains humus and small grains of rock. It has undergone the greatest number of changes from the underlying rock layer. In your science log, suggest how leaching fits into the rock cycle. The next layer, B is generally lighter in color because there is little or no humus, and it contains minerals that have leached from the top layer. Leaching is the removal of soil materials dissolved in water. Water reacts with humus to form an acid. This acid can dissolve elements and minerals from upper layers and carry them through the spaces in the soil to lower layers. In your science log, suggest how leaching fits into the rock cycle. The bottom layer C contains partially weathered rock and minerals leached from above. This layer most closely resembles the original or parent rock below and is at the beginning of the long, slow process of rock evolving into soil. Soil can be very deep. When you build a bridge, for instance, the Brooklyn Bridge in New York on the East River, on the east side of Manhattan, lower Manhattan, one side is on rock. They had to drill down. They had to dig out the river. And the other side was just too deep. They just got tired of it, and they just put that end of the bridge on soil. It's not on rock. The bridge is so heavy, it's fine. But buildings oftentimes will drill down through the soil, and sometimes it's very, very deep. When I was younger, we lived on property that had once been a farm, and the soil was very rich. It was very, very dark, almost black, very dark, and that was because of the humus. So you have in figure 1024 exposed soil profile of an eroded hillside, and the markings of A, B, and C coincide with the text. Soil texture. Texture relates to how soil feels when it is rubbed between two fingers. Texture can tell us much about the soil, what is in it, and what it can do. The formation of topsoil depends largely on the particle size of the rock fragments. See table 10.3. Name of rock sediment: gravel, over 2 millimeters in diameter. Sand, 2 to 0.05 millimeters in diameter. Silt, 0.05 to 0.002 millimeters in diameter. And clay, less than 0.002 millimeters in diameter. The particle size affects how gritty a soil feels when you rub it between your fingers. It also determines how large the spaces will be in the soil. As you have just seen in the previous investigation, all these factors affect how quickly water will drain through or permeate the soil. If the soil is sandy, rainwater permeates it too quickly. This kind of soil has a low water holding capacity. Water holding capacity refers to a soil's ability to hold water. Soil with low water holding capacity tends to be dry or arid most of the time. Clay particles, on the other hand, are so small that they fill up most of the spaces in soil, leaving little room for air and water. Rainwater often sits on top in puddles and soaks in very slowly. Clay has a high water holding capacity. To grow most plants, topsoil should allow water to drain through it at a moderate rate. Farmers and gardeners prefer a mixture of sand, silt, and clay, a type of soil referred to as loam. Farming, soil loss, and the environment. Soil is an important resource in Canada and throughout the world. When vegetation is removed by harvesting crops, the soil is exposed to the direct action of rain and wind. Topsoil, which contains the nutrient rich humus can be eroded and carried away through weathering. Also, without plants, soil development slows and sometimes stops because humus is no longer being produced. When natural vegetation is removed from land that receives little rain, plants do not return. All of these conditions can contribute to the destruction of the natural ecosystem and lead to desert formation called desertification. This is currently happening on every continent, especially in the rainforests along the equator in South America, Amazonia, and in Central Africa. While modern farming methods are capable of feeding billions of people on Earth, they can contribute to the destruction of the very environment that is needed for such large-scale farming. Productivity has increased through the use of large agricultural machinery and agricultural chemicals. Large-scale operations can take their toll on the environment, however. Large equipment requires that farmers plow long, straight lines. This can contribute to loss of topsoil due to water erosion. Trees that are used as windbreaks often have to be cut down to make larger fields, which can expose the field to loss of topsoil due to wind erosion. In many cases, marshes have been drained and fields plowed right to the edge of rivers and streams. This can contribute to the elimination of different species of wildlife. The machinery used in large-scale agricultural operations relies on the combustion of fossil fuels, which adds to air pollution. Nitrogen compounds and other substances in fertilizers and manure, as well as chemicals in the widespread application of pesticides and herbicides, dissolve in water and find their way into the rivers, streams, and groundwater systems. The result is the pollution of human drinking water. How can farmers minimize the damage? Saving the soil. Most farmers try to prevent soil erosion and to minimize the environmental impact of their farming practices. If they have had to remove windbreaks, they plant new ones in locations suitable for their fields. As well, they cover bare soils with decaying plants to hold soil particles in place. In dry areas, instead of plowing the natural vegetation under the soil to plant crops, farmers graze animals on the natural vegetation. Proper grazing management can retain plants and reduce soil erosion. In recent years, many farmers have begun to practice the no-till farming, figure 10.25. In no-till farming, old plant stalks are not removed. Where I grew up in New Jersey in the United States, corn crops are not plowed under, not like they used to be in the old days where they would be removed and completely and then plowed under again. They're often left to rot in the fields and then seeded right over them with very, very minimal plowing. Normally, farmers till or plow their fields 2 or 3 times a year, exposing the topsoil to dangerous wind erosion each time. In no-till farming, plant stumps are left in the fields. At the next planting, farmers seed crops without removing these stalks and without plowing the soil. No-till farming provides cover for the soil all year round and reduces soil erosion. Landfills and buried waste. You have seen that we use land for mining and for farming. You also know that we build our towns and cities on much of it. This urbanization leads to another use, landfill sites. Garbage is a part of modern life. Most garbage is brought to a landfill site, an area where waste is deposited. See figure 10.26. There, the garbage is dumped, sorted, and eventually buried. A great percentage of the volume of garbage brought to landfills is dry, relatively harmless garbage, or kitchen and garden waste that can decompose and contribute to the humus content of the soil below. Figure 10.26, hazardous waste can find its way into landfill sites. Although hazardous waste is supposed to go to specific sites, it sometimes ends up in landfill sites. Hazardous waste includes various types of poisonous substances that can seep into the ground and into our water. Underground gasoline tanks and septic systems can leak, as well as runoff from farm fertilizers also flow into our water system. Land developers have learned to be careful about choosing locations for landfill sites. They first take into account the nature of the garbage that will be buried there. Then they examine the soil and rock formations in the area, which types of soil and rock would minimize the leaching of poisonous chemicals through the ground. Although hard rock and clay can minimize leaching, there will never be a permanent solution to the storage of the more dangerous wastes. You can help by reducing the quantities of harmful materials that you use and throw out. You and your family can separate hazardous waste from the regular garbage and take it to the appropriate collection site. Land is one of Canada's great resources. It contains the rocks and minerals we need for construction and industry. It grows our food, produces our mineral resources, and provides beautiful settings for our towns and cities. It is where you live and go to school. It is where your future lies.